I think what I'm going to do, instead of spending several class periods going through Hardy-Weinberg problems, is I will go through, we've gone through numbers 1 and 2 in class. I think tomorrow we'll take some time and go through 3 and 4. And so I'm going to create a quick video here to start us with problem 5 and then work our way through number 9. And so I'm just going to pull up a Smart Notebook document here, and we're going to work our way through these problems. And you have the problems in front of you, and so we'll go from there. All right, so let's start with number 5. It says a rather large population of biology instructors have 396 red-sided individuals. Okay, so I'll put that in there. 557 tan individuals. And anytime they give us numbers like this, I always like to total them. So I have 953 total, just because usually that's something that comes in handy. Okay, we're assuming that red is totally recessive. So if we do this for little r, then we can kind of work through the rest. So the first thing you need to say is, okay, how do we create a frequency? So if I know little r, that's the same as q squared, right? And so if let me put our equations up here. So p plus q equals 1 is for your allele frequencies. P squared plus 2pq plus q squared equals 1 is for genotypes. And so what I know with r squared is this q squared down here in the second equation. And so I can figure out a frequency by taking 396 and dividing by the total. Okay? And so when I do that, I get little r equals 0.42. And then from there, I can figure out P and Q, right? And so A asks you for the allele frequencies of each of little r and then big R. And all I need to do is find Q to do that. And so right now I know Q squared. So in order to find Q, I take the square root of both sides, right? And I get Q, which is also R, is equal to 0.65. All right, and then if I plug that into this first equation here, I have a 1 minus 0.65 gives me P, which is our dominant allele, and I have 0.35 for that. So that is part A. When we look at B, it's asking for the expected genotype frequencies. Sorry, that was me moving the stool. And if we already know, hold on one second. All right, so if we already know little r, right, that is our q squared. So we know this one. And now what it's asking us to do is figure out p squared, which is big R, big R. Okay, so if I want to do big R, I come back down and I look at this number here, and this is p. So essentially, I just square it. And so I can get big R, if I square that, is 0.12. Okay, now if I go to this next part of the equation, which is 2pq, that's for the heterozygous individuals. If I take P, so we have 2pq, so I take 2 times 0.35 times 0.65, which is Q, I end up with a total of 0.46. And so if you haven't done so already, make sure you try that so you understand where that comes from. C is looking for the number of heterozygous individuals you would predict to be in this population. So this one's a little tougher because I know if I switch colors here and go back up here, I know that 557 are tan, I know that 396 are red, and I know I have 953 total. And so what I can do is I can take this total number, and I can take this, which is the frequency of heterozygotes in the population, and I can actually multiply them, okay? And so for C, if I take 0.46 times 953, I get roughly 439 for the number of individuals, okay? For D, it's asking for the expected phenotype ratios. Let me extend this page here. So for phenotype ratios, what I'm assuming is that big R something is going to give us tan individuals. Little r gives us red. And so I already know that little r is 0.42. And so this is going to be the red phenotype. Okay? To get the tan phenotype, if I know they're either tan or red, really I can just take 1 minus 0.42, and that gives me the tan, which is 0.58. Now another way that you could figure that out is you could add 0.12 to 0.46, because that's including your homozygous dominant and your heterozygote, and that gives you 0.58 as well. Okay, so that's D. E says conditions happen to be really good this year for breeding, and next year there are 1,245 young potential biology instructors. Assuming that all of the Hardy-Weinberg conditions are met, which means that your population would be in equilibrium, how many of these would you expect to be red-sided and how many tan-sided? And so essentially, you can take these phenotype frequencies, multiply them by the new total, which is 1,245, and you get roughly 722 tan and 523 red. So make sure you're actually trying these calculations as we go through and making sure it all makes sense to you. All right, now if we extend the page and we go to number 6. Okay, this problem says a very large population of randomly mating laboratory mice contains 35% white mice. So I know something is going to be 0.35. White coloring is caused by the double recessive genotype a. So I know that this is true. This is a frequency, which is the same as q squared. Calculate allelic and genotypic frequencies for this population. Okay? So what it's asking for is a, which we already have. It wants big A, it wants big A. So these would be all of our genotypes, right? This is 2pq, this is p squared, okay? But then it also wants the alleles. And so it's also asking for what is A, which is q, and then what is big A, which is p. Okay? And because it gives us little a, once again, we can figure this out really quickly by just taking the square root of this part right here. So if we take the square root of 0.35, we get 0.59. Okay, so now I know A. If I know little a, I can figure out big A, because remember, p plus q equals 1. So all I have to do is take 1 minus 0.59, and I should get 0.41. And if I know both of these numbers, I can easily figure out the rest. So if I know 0.41 and 0.59, I can say 2 times 0.41 times 0.59 equals, and I should get, I think, 0.48 for my heterozygotes. And then if I know that big A is p squared, then I can just say, all right, 0.41 squared equals, and I have roughly 0.17. And so that's problem number 6. Okay? Let's switch gears and go to problem number 7. After graduation, you and 19 of your closest friends, so we have 20 total, 10 males, 10 females, charter a plane to go on a round-the-world tour. Unfortunately, you all crash land safely on a deserted island. No one finds you, and you start a new population totally isolated from the rest of the world. 2 of your friends carry, i.e. are heterozygous for, the cystic fibrosis allele. And so I know that 2 out of 20 individuals, which is equal to 0.1, carry this recessive allele, which makes them heterozygotes. Okay? Assuming that the frequency of this allele does not change as the population grows, what would be the incidence of cystic fibrosis on your island? Now, when we do this one, so we know 2PQ. Now, this is where it gets kind of dicey because when I know 2PQ, how am I supposed to separate those? And so with this problem, you have to make a couple of assumptions. You have to assume that the rest of the individuals are healthy. You have to assume that I would have told you if there was any people who had cystic fibrosis there. So we are assuming that completely recessive, homozygous recessive is not present. And if we assume that, then we can assume that homozygous dominant makes up 0.9 of our population because heterozygous made up 0.1. And so this is kind of the key assumption that you have to use to go into this problem. So if I'm assuming that big C is 0.9, oops, I know that's p squared, okay? And if I know that's p squared, then I can take the square root of both sides of this equation to figure out, well, big C, which is p, which would be 0.95. So this kind of makes sense that 95% of the population would be carrying that big C allele. And if I know that big C is 0.95, then I can say, okay, I have little c is q, 1 minus 0.95 is 0.05, and this is going to make up those recessive alleles. And people say, well, there is no recessive alleles. You already said that little c is 0, but we have to account for the recessive allele that's in this heterozygote, okay? And so this is assuming that the frequency of this allele does not change as the population grows, what will be the incidence of cystic fibrosis on your island? And so now that we have both of these numbers, we now need to say, okay, if this stays the same, what are my chances of getting cystic fibrosis? And so I want to calculate now, what are my chances with these numbers of getting q squared? And if I take 0.05 and I square it, because this is q, I get 0.0025, which is the same thing as 0.25%. So there's a very small chance that you're going to have cystic fibrosis on your island. Okay? All right, let's look into number 8 here. Okay? Number 8 is also dealing with cystic fibrosis. It's a recessive condition that affects 1 in 2,500 babies in the Caucasian population. Calculate the frequency of the recessive allele. Well, if I know 1 in 2,500 babies, right, then I know this is equal to little c, okay, which I know is also equal to q squared. And so I know if I figure this out, it's 0.0004. And if I know q squared, I can take the square root of both sides and figure out that q equals 0.02. And if I know q, then I can figure out p, which is the dominant allele, by taking 1 minus 0.02, which gives me 0.98. So I know that my recessive allele is q, my dominant allele is p, and C asks for the percentage of heterozygous individuals or carriers in the population. And so if I know Q and P, I can figure out heterozygotes by taking 2 times 0.02 times 0.98, which gives me 0.04, which is roughly 4% of the population. Okay? And then for our final problem here, we're going to do number 9. Okay, this says the ability to taste PTC, like we did in those paper strips, is due to a single dominant allele, big T. So that means that big T anything can taste PTC. You sampled 215 individuals in biology and determined that 150 could taste the bitter taste of PTC and 65 could not. Okay, so this is kind of tricky because what you're saying is big T something corresponds to 150 out of 215. But I can't use that to figure out big T or my P because I can't separate the heterozygotes from the homozygous, or I'm sorry, yes, from the homozygous dominant at this point. So what I need to focus on is the idea that 65 of the 215 could not taste it. And this makes them little t, which is our q squared. Okay? So if I know this is q squared, and if I work this out, and this equals 0.3, I can take the square root of both of these. I get q, which is little t, equals 0.55. And then from there I can figure out p, which is big T, by taking 1 minus 0.55, which gives me 0.45. And from there I can figure out everything else. And so it wants all potential frequencies. So now it's asking for big T, which is p squared. So if I take 0.5 and I square it, I get 0.2. And then the big T, little t is 2pq, which means I take 2 times 0.55 times 0.45. And if you work that out, you should end up with 0.5. And hopefully that all made sense, and you understand how to work through those problems. Hardy-Weinberg is really useful when you are predicting future generations, kind of like in problem 5, where we said, okay, now we have 1,245 biology instructors. What do we predict? And you can look at number 7, where we say as the population grows, how many individuals are going to have cystic fibrosis? This is why we use Hardy-Weinberg probability, because if your population is in Hardy-Weinberg, if all of those 5 conditions are met, if there are no agents of evolution in action, then you should be able to use these numbers to predict. Now, if you predicted 4% would have cystic fibrosis, like in number 8, and 20% had it, then what does that tell you? That tells you that your population is not in Hardy-Weinberg equilibrium, that it is evolving, that there's some agent of evolution in play, and then you ask questions from that point on. Okay? Let me know if you have any questions, but there you go.